Hi everyone, my name is Khalil Hachem. I'm a Ph.D. candidate in civil engineering at McGill University. I've been working with Professor Mary Kang for 3 years now. Our research focuses on environmental impacts of energy development. In particular, I'm interested in methane and hydrogen sulfide emissions from oil and gas wells. Today, I'm going to be talking about methane and hydrogen sulfide emissions from abandoned, active, and marginally producing oil and gas wells in Ontario. So to start, why do oil and gas wells emit gases? So oil and gas wells are subsurface structures that connect oil and gas producing formations to groundwater aquifers, other subsurface formations, and the atmosphere. In some cases, due to structural deterioration, oil and gas wells may serve as leakage pathways for subsurface formation fluids to leak to groundwater aquifers or the atmosphere when the well is either active or when the well is abandoned. In this work, we focus on 4 categories of wells. The first 2 types of wells are abandoned wells, abandoned plugged, and abandoned unplugged. And abandoned wells are wells that no longer produce hydrocarbons. Whereas the second category of wells are producing wells, and we divide them into 2 types of wells, marginal wells and active wells. Both of these wells produce hydrocarbons, but the differentiation is in the amount of gases or oil they produce. So marginal wells produce 1,700 meter cube of natural gas per day or 1.6 meter cube of oil per day or less, whereas active wells produce more than 1,700 meter cube of natural gas per day or more than 1.6 meter cube of oil per day. Oil and gas wells actually emit a lot of gases to the atmosphere, including methane, H2S, ethane, propane, volatile organic compounds. But in this work, we focus on methane and H2S emissions. The reason for that is that methane is a very potent greenhouse gas, and the emissions of 1 kilogram of methane is the equivalent of emitting 28 kilograms of carbon dioxide. So it's really important to know where these methane emissions are coming from, try to reduce them in order to limit the impacts of climate change. Moreover, methane emissions from abandoned wells are the most uncertain category in Canada's National Inventory Report. And the authors of this study highlight that this uncertainty is because there are very few measurements of methane emissions from oil and gas wells in Canada. Now we focus on hydrogen sulfide because hydrogen sulfide is a highly toxic gas that can be deadly to humans and animals and very damaging to the natural environment. Moreover, H2S emissions from oil and gas wells are not accounted for in Canada's air pollutant inventory. And that is because prior to this study, there were no available data or no available measurements on H2S emissions from oil and gas wells. Now, you may wonder, why are we focusing on oil and gas wells in Ontario, although there are other oil and gas producing provinces in Canada, such as Saskatchewan, Alberta, BC. So oil and gas exploration in Ontario started in the mid-19th century, and it led to an oil rush in the 1860s and 1870s, and it resulted in thousands of wells being drilled. So these wells are really, really old, like one of the oldest in the world. So this oil rush resulted in thousands of wells being drilled, and 27,000 of these wells are documented. And it's estimated that 30,000 wells are undocumented. And this is really important because these wells do exist, and they are like boreholes in the earth that reach subsurface formations. But the ministry have no idea where these wells are, what are their attributes, which fluids used to produce, nothing. Although they emit gases, we know nothing about them. So I also mentioned that oil and gas wells in Ontario are really old, and this is also another important factor because in the past, industry standards were not similar to industry standards today, especially when it comes to plugging. So in the past, they used to plug wells with tree trunks and rubble, and today we know that plugging wells with tree trunks and rubble is not an effective method to reduce or to stop leakage pathways. So in this slide, we see it's a picture of a plugged well. So this well is labeled as plugged in the Ontario Oil and Gas Wells database. However, it's unplugged, and it led to the formation of this pond. This pond is basically sulfur water, which is water that is really rich in hydrogen sulfide. In this picture, we don't see any environmental damage because the damage is actually on the other side of the pond, but it doesn't appear in the picture. So in terms of the methods that we use to conduct our measurements, we use a static chamber methodology, which involves building a chamber enclosing all above ground infrastructure of the well. So if this is the well, we build a chamber that encloses all of the well, and then we measure the change of concentration of the gases inside the chamber. Now, this change of concentration of the gases is going to be attributed to the well itself because this is the only component inside the chamber that may or may not be emitting. So we measure the concentration of gases inside the chamber for a duration of 10 to 15 minutes. And then we fit a linear model to this data. And this is actually shown in this chart here. The slope of this model represents the change of concentration of methane or of other gases over time. And from the change of concentration of gases over time, we can compute the change in mass over time. And this is actually the emission rate. For example, 10 kilograms of methane per day, or this is a random value, or like, so this is the value that is used to inform greenhouse gas inventories and air pollutant inventories. To measure the concentration of gases inside the chamber, for methane, we use two analyzers, the portable methane detector and the Picaro G4301. Now we use two different analyzers because the PMD, or the portable methane detector, is really good for high emitters. It has a very high detection range, up to 50,000 ppm. However, it's really not sensitive at low concentrations. If the concentration of methane is below 10 ppm, the PMD is going to display zeros throughout the measurement duration, and we're going to assume that this well is emitting 0 milligrams of methane. However, the Picaro is a much more sensitive analyzer, and even if the concentration of methane inside the chamber is less than 10 ppm, we can see how this concentration is increasing or sometimes decreasing, and then we can compute slightly positive or negative emission rates. To measure the concentration of hydrogen sulfide, we use the BW Ultra multi-gas detector. Now, this detector can measure methane, H2S, carbon monoxide, oxygen, and carbon dioxide, but we only focus on its H2S measurement capabilities to compute H2S emission rates. In terms of results, in this chart, we can see that highly emitting abandoned, marginal, and active wells all emit in the same order of magnitude. Like we can see that they emit at around 10 to the power 4.5 milligrams per hour. We also find that H2S emitting wells are the highest methane emitters. And this finding is really important because there's a potential that there's a lot of H2S emitting wells, not only in Ontario, especially in Western Canada. And if there is a correlation between H2S and the methane emission rates, it's important to know this. And then this can inform future field campaigns and future measurement campaigns to get a better representative samples of the wells. We also compare our average emissions to emission factors used in the Canadian National Greenhouse Gas Inventory. And we find that methane emissions from plugged abandoned wells in Ontario are underestimated by a factor of 920. And active and marginal wells are underestimated by a factor of 2.1. So it's really important to note that the Canadian inventory used data that was collected in the US. And the conditions of oil and gas wells in the US may not be representative of the oil and gas wells condition in Ontario or elsewhere in Canada. And that is because like some wells produce from different basins, some wells may be producing oil, some other wells may be producing gas. And also legislation is a very important factor in emissions. So for example, if there's a state where they don't have any mandates on monitoring and repair, we expect that they are going to have much higher emissions compared to states with good policy and monitoring and repair strategies. So to capture a full image of how methane emissions from abandoned and suspended oil and gas wells look like in Canada, we need to collect measurements from all oil and gas producing regions. Concerning H2S emission rates, we were able to find H2S at 3 wells, and one of them is unplugged, one of them is plugged, and one of them is potentially undocumented. And I say potentially undocumented because we're not 100% sure whether that was a well or not. However, it's highly likely that it's a well. And I say it's highly likely because we conducted different measurements in this wetland area where the undocumented well is. So we conducted different measurements and we found emissions at only one spot. Now, if these emissions were from a natural source, we would expect to see the emissions in all or multiple spots in the wetland. However, we found them in a specific spot. And we say that this well is potentially undocumented because in the library, there are no records of any wells existing in this wetland. We also study well attributes affecting methane emissions, and this is very important in order to understand which well parameters are associated with high methane emissions. This can help in concentrating mitigation efforts to target high emitters. As expected, we find higher methane emission rates at unplugged wells compared to plugged wells. We also find that the well operational status, active, abandoned, or marginal, affects methane emissions. We also find that wells plugged before 1997 emit at a much higher rate compared to wells plugged after 1997. And we chose the year 1997 as a cutoff because in this year, the Oil and Gas Resources Act became a law in Ontario. We also find that higher methane emission rates in regions with high well densities and find a correlation with the well longitude and the measurement county. Now, the correlation with the well longitude and the measurement county may be attributed to geology because these wells may be producing from different pools and different target formations. We also study the meteorological factors and seasonal variability of the emissions. We got meteorological factors from the Welland-Pelham weather station, and that was the closest weather station to our measurement region that provides detailed hourly data. We find negative correlation with the amount of daily precipitation, meaning that the higher is the precipitation on a specific day, the lower are the emissions. However, we find no correlation with temperature, dew point temperature, relative humidity, atmospheric pressure, and wind speed. Concerning seasonal variability, we conduct 40 measurements in 2 different seasons on 20 wells, and in October 2020 and February 2021. And from this chart, we can, the general finding is that high emitting wells remain high emitting in different seasons, and they usually emit at the same magnitude, although in some cases they differ. We also study the role of natural methane sources to determine whether the leaking methane is of thermogenic or biogenic origins. So thermogenic methane is basically methane found in oil and gas formations, and biogenic methane is methane produced in the shallow subsurface. So thermogenic methane, the leakage of thermogenic methane is often associated with human activities, whereas biogenic methane emissions are not associated with human activities. So to do that, we study concentration of ethane in gas samples collected from the chamber and the carbon isotopes of methane. So we chose to study ethane because ethane is not co-produced with biogenic methane, but it's co-produced with thermogenic methane. And in this chart, we see that as the emission rates increase, the value of the ratio of ethane to methane increases. This means that as the emission rate increases, it's more likely that they are coming from a thermogenic source. The same applies to the carbon isotopes of methane. We see that as the emission rates increase, we tend to have methane that is more enriched in carbon-13. And this means that this methane is thermogenic, because if the methane was biogenic, we would expect that it's more enriched in carbon-12 because the bacteria prefers lower weight carbon compared to higher weight carbon. To recap what I said, it's very important to determine the number of H2S emitting wells in Ontario and elsewhere, because the potential occurrence of H2S at many oil and gas wells means that oil and gas wells may be a significant source of H2S emissions, and this actually requires further study. Also, conducting additional measurements from H2S emitting wells is essential to understand the relationship between H2S and methane emissions to accurately estimate greenhouse gas inventories in Canada and the United States. And I mentioned also the issue of undocumented wells. So in our study, we found that undocumented wells, although it's only one well, we found that it's emitting a substantial amount of methane and H2S. However, these wells are not included in inventory well counts, so they are not considered as emitting. And this is something that also requires further study. Also, regulatory oversight to ensure that all wells are licensed, which allows for uniform testing to all the wells. This reduces the risk of leakage and emissions due to improper maintenance. These are our references, and I'll be available during the panel for any questions. Thank you.